3 weeks into this build, I'm watching my monitoring dashboard at 3 a.m. and everything's red. Not amber, not yellow, full crimson. The inference endpoint that was handling maybe 200 requests an hour during testing is now getting hammered with 3,000. Latency spikes to 40 seconds. Users are churning in real time. And I'm sitting there realizing that everything I thought I knew about deploying ML systems was basically theoretical nonsense. That moment right there, that's actually where this video starts. Because over the past 30 days, I built a complete AI SaaS from the ground up. Not a tutorial project, not a weekend hack, an actual production system serving real users. And I documented everything. Every architecture decision, every infrastructure choice, every catastrophic mistake. This is the full technical breakdown. No fluff, no hand-waving. We're going deep on the stuff that actually matters when you're trying to ship something real. If you've built toy projects and you're wondering what the gap looks like between that and production, this is your answer. Let's get into it. All right, let's talk architecture. The obvious choice here would have been to reach for something like Vercel plus a managed ML endpoint, maybe Replicate or Modal. And honestly, for prototyping, that's fine. But I had specific requirements that ruled that out immediately. First, I needed sub 200 millisecond inference latency for the core feature. We're doing real-time document analysis. Second, I needed to handle burst traffic patterns where you might get nothing for an hour, then suddenly 500 concurrent requests. Third, and this is the kicker, I needed to run fine-tuned models that aren't available on any managed platform. So the stack I landed on, FastAPI for the API layer, obviously. Kubernetes on GKE for orchestration because I needed the auto-scaling granularity that you just don't get with simpler platforms. Redis for caching and as a message broker for async jobs. Postgres with pgvector for the vector store because maintaining a separate Pinecone instance felt like unnecessary operational overhead for my scale. And then model serving through a custom setup using vLLM, which we'll get into. The controversial choice here wasn't using Lambda or Cloud Functions for the API. The cold start problem isn't just about latency, it's about consistency. When you're doing ML inference, you need the model weights loaded and warm. A cold start means you're waiting for a multi-gigabyte model to load from storage. That's not milliseconds, that's seconds. Sometimes double-digit seconds. For my use case, that was disqualifying. So instead, I went with persistent containers that stay warm, auto-scaling based on actual request patterns rather than reactive scaling. The trade-off is you're paying for idle capacity, but we'll talk about how I minimize that later. Now the data pipeline. This is where most tutorials completely fall apart because they show you how to process a CSV, not how to handle a fire hose of unstructured documents coming in at unpredictable intervals. The system ingests documents from multiple sources, direct uploads, webhook integrations from various platforms, and a batch import system for enterprise customers. Each path has completely different characteristics. Direct uploads are synchronous. Users are waiting, you need to process fast. Webhooks come in bursts and can back up. Batch imports might drop 50,000 documents at once. I architected this as a 3-stage pipeline. Stage 1, validation and normalization. Documents come in, get validated against format requirements, normalized into a consistent internal representation. This happens synchronously for direct uploads, async for everything else. Stage 2, extraction and chunking. This is where the actual ML processing happens. OCR if needed, text extraction, semantic chunking with overlap. I'm using a sliding window approach with 512 token chunks and 50 token overlap. Stage 3, embedding and indexing. Generate embeddings using a fine-tuned version of bglarge, then index into pgvector. The critical insight here is that stages 2 and 3 don't need to block the user. Once stage 1 completes, you return a job ID and process the rest async. But you need robust queue management. I'm using a priority queue system where direct uploads get priority 1, webhooks get priority 2, batch imports get priority 3. And here's the thing no one tells you. You need back pressure mechanisms. When your queue depth exceeds a threshold, you need to start rejecting or rate limiting incoming work. I learned this the hard way when an enterprise customer dropped a 100,000 document batch import while we were already processing a backlog. The queue depth hit 2 million items, memory usage spiked, and workers started getting OM killed. Fun times. Now I have circuit breakers at every ingestion point. Let's talk model serving because this is where that 3 a.m. incident happened. Initially, I was running the model through a basic FastAPI endpoint with a model loaded directly in the web process. Classic mistake. Works fine in development, completely falls apart under load. The problem is Python's GIL. When you're doing inference, that process is blocked. Concurrent requests queue up. Latency compounds exponentially. The solution is to separate your model serving from your API serving. I moved to vLLM, which is purpose-built for this exact problem. It handles continuous batching, which means instead of processing requests one at a time, it batches them together efficiently. This alone dropped my P99 latency from 8 seconds to under 200 milliseconds. But containerizing vLLM properly is its own adventure. You need CUDA drivers in the container. You need to handle GPU memory allocation carefully because if you overallocate, you get OM errors. Underallocate, and you're leaving performance on the table. I spent probably 40 hours just on the Docker file and Kubernetes resource specs. Some specific numbers that might save you time. For a 7B parameter model, I'm allocating 24 gigabytes GPU memory with a 90% utilization target. The container needs about 16 gigabytes of regular RAM for the CPU side operations. I'm using tensor parallelism across 2 GPUs for the larger requests. Auto-scaling triggers when average GPU utilization exceeds 70% for 60 seconds. Scale down has a 10-minute cooldown to avoid thrashing. One more thing. You absolutely need health checks that actually verify the model is loaded and responding, not just that the container is running. I've seen containers pass basic health checks while the model was stuck in a deadlock state. My health check endpoint does an actual inference call with a cache test input and verifies the response. Authentication and multi-tenancy sound boring until they break, and suddenly you're explaining to a customer why their data might have leaked to another customer. I'm using a pretty standard JWT setup with refresh tokens, but the multi-tenancy layer is where it gets interesting. Every request carries a tenant ID derived from the JWT. This tenant ID is used to partition data at the database level. Every table has a tenant underscore ID column, and row-level security policies enforce isolation. Sounds straightforward, but the devil is in the details. What happens when your background workers need to process jobs across tenants? They need elevated permissions, but you also need audit trails. What about your vector database queries? Vector doesn't have native row-level security, so I'm handling tenant filtering at the application layer with a middleware that injects tenant predicates into every query. But here's where it gets really tricky: caching. Redis doesn't know about tenants. If you're not careful with your cache key structure, you'll accidentally serve tenant A's cache data to tenant B. My cache keys are structured as tenant underscore ID, resource underscore type, resource underscore ID. Every cache read validates that the tenant underscore ID in the key matches the request context. It adds overhead, but the alternative is a data breach. For enterprise customers, I also implemented a bring your own key encryption scheme. Each tenant can provide their own encryption key, and their document contents are encrypted at rest with that key. The keys are stored in a separate KMS, never in the application database. This adds meaningful latency to every document operation, but for regulated industries, it's non-negotiable. This is the section most developers skip because it's not sexy, and then they're flying blind when things go wrong. Observability isn't optional. Full stop. My stack: Prometheus for metrics, Grafana for dashboards, and OpenTelemetry for distributed tracing. Every API request gets a trace ID that propagates through every service it touches. When something goes wrong, I can pull that trace and see exactly where the request spent time, what database queries it made, what cache hits or misses occurred, how long inference took. The metrics I actually care about: request latency percentiles, P50, P90, P99, error rates by endpoint, queue depth and processing time, GPU utilization and memory, and cost per request. That last one is crucial. I built a custom metric that calculates the estimated cost of each request based on compute time, GPU seconds, and storage operations. This feeds into an alert that fires if cost per request exceeds a threshold, which usually indicates something is inefficient. For logging, I'm using structured JSON logs that go to a central aggregator. Every log entry includes the trace ID, tenant ID, and relevant context. You'd be amazed how often a production issue is solved by grepping logs for a specific trace ID. The alerting philosophy I've landed on: alert on symptoms, not causes. I don't alert when CPU hits 80%. I alert when latency exceeds SLOs. High CPU that doesn't affect users isn't an incident. The exception is resource alerts that indicate imminent failure, disk space, memory pressure, those kind of things. Let's talk money because this is where the theory of cloud architecture meets the reality of your bank account. My initial deployment cost around $2,400 per month. For a side project SaaS, that's borderline unsustainable. Here's how I got it down to $340. First, right sizing. I was running way more capacity than needed because I was scared of that 3 a.m. incident happening again. But once I had proper auto-scaling and monitoring, I could confidently reduce baseline capacity. The minimum replica count went from 4 to 1 for the API layer, 2 to 1 for model serving during off-peak hours. Second, spot instances. For the model serving nodes, I'm using preemptible GCE instances that cost about 60 to 70% less than on-demand. Yes, they could be terminated with 30 seconds notice, but with proper graceful shutdown handling. In-flight requests complete before termination. I've been running this way for 3 months with zero user-visible impact from preemptions. Third, caching and deduplication. A huge portion of my inference calls were actually identical requests from the same tenant. Implementing a semantic cache where similar queries return cache results cut my inference costs by roughly 40%. Fourth, time of day scaling. I analyzed my traffic patterns and built custom scaling schedules. Between 2 a.m. and 6 a.m. my time zone, traffic drops to basically nothing. I scaled down to absolute minimum during those hours. The biggest single savings came from reserved capacity commitments for the resources I know I'll always need. GCP gives you significant discounts for committed use, and once your baseline is stable and predictable, there's no reason to pay on-demand rates for that baseline. So what would I do differently if I started this project tomorrow? First, I would start with better abstractions for multi-tenancy from day one. Retrofitting it was painful. The data model should assume multi-tenancy even if you only have one tenant initially. Second, I would invest in integration tests earlier. I had solid unit tests, but integration tests that exercised the full pipeline caught bugs that unit tests completely missed. Things like subtle timing issues in the async processing, race conditions, and cache invalidation. Third, I underestimated documentation. Not public docs, internal docs. 6 months from now, when I've forgotten why I made certain decisions, I need to be able to understand my own architecture. I've started keeping an ADR, architecture decision record, for every significant choice. Fourth, I would have used infrastructure as code from the very beginning instead of migrating to Terraform halfway through. The migration was disruptive and error-prone. Where does this go from here? The roadmap has 3 major items. First, a proper CI/CD pipeline for model updates. Right now, deploying a new model version is manual and nerve-wracking. Second, multi-region deployment for lower latency globally. Third, usage-based billing infrastructure because the current flat-rate model doesn't scale economically. That's 30 days of building compressed into this video. The gap between tutorial projects and production systems isn't about any single technology. It's about the compound complexity when everything has to work together reliably at scale while costing a reasonable amount of money. If you're planning your own build, I hope this gave you a realistic picture of what's actually involved. The code patterns and architecture decisions here are hard-won from actual production failures. Take them, adapt them, learn from my mistakes so you can make your own new and interesting mistakes instead.